Hey guys, so today our video is just more of a review, and we're going to be applying some concepts for scientific notation and the operations with scientific notation. So again, this week the information isn't completely new to you. You're not going to be learning something in this video that you haven't seen before. We're just applying the information we already know to a new situation. And some of the examples I give you are actually very specific to science itself. I know that I had a few students ask if they could use scientific notation in science class when they're working on things with the Earth and the Moon and the layers and all of that, and that's fine. Ms. Mers also would like to see you do that. So for today's video, your W, as always, you're going to watch. Today you're going to have to pause and rewind from time to time in order to copy down the problems and possibly go through the example again, see how I set it up. Secondly, you're going to have to summarize. So again, copying down the problems. I'm going to do one with you, and then there's two more for you to do on your own. You need to make sure that not only do you have the words written down, but that you're also showing your work and solving the problem, and your answer should always be in scientific notation. And then lastly, you're going to create your own problem. It's original, so it can't be one we've already used. And it should be in scientific notation. You can use any operation you choose. So it could be addition, subtraction, multiplication, or division. I'm going to ask that you have the answer to your problem already somewhere written down, but tomorrow when you come to class, we're going to jump right in by sharing some of these problems and working together on them. Okay? So your first problem, it's very small. I apologize for the small font, so I'll zoom in. Okay, I'm having trouble finding it. Not working. Hold on. All right. The distance from the Sun to Andromeda Galaxy is 1.2 times 10 to the 19th miles. Light travels at a speed of 5.88 times 10 to the 12th miles per year, called a light year. How long does it take light to travel from the Sun to Andromeda Galaxy? So this is the problem we're going to solve together. It's up there. It's small, but if you paused it, copied it down, you should have it. Okay, so there it is on the screen. Again, if you need to pause, rewind to make sure you have it copied down correctly, go ahead. So I have two numbers here, and since we've been doing operations in scientific notation, we should know at this point that we're doing something with those two values. So we have this amount of miles, and we have miles per year. Cut that off a little bit, it's there. And that's a light year when we're talking about how many miles per year light travels. And we're looking for how long it's going to take for light to travel from the Sun to Andromeda Galaxy. So again, I will write this larger, 1.2 times 10 to the 19th miles. And it travels at a speed of 5.88 times 10 to the 12th miles per year. On the screen, good. So I need to decide what operation I'm going to use. When I'm thinking about this problem, these numbers are often not realistic to us and what we experience day to day. So I like to put things in a scenario that is realistic to me. So I might start with the example, the distance from my house to school is 10 miles. And I am traveling at a speed, let's say I ride my bike to school. So I'm going to be traveling at a speed of 5 miles per hour on my bike. And I would like to know, that's actually pretty slow. Maybe I'm walking to school, I suppose, but we'll see. I would like to know how long it's going to take me to get to school. Well, if I have a distance of 10 miles, and every hour I'm going 5 miles, then I can divide that out. 10 miles divided by 5 miles in an hour, and I could see that it would take me 2 hours to get to work by walking or riding my bike, because that's pretty slow, 5 miles per hour. Hopefully I'm not driving my car 5 miles per hour. So again, I would do 10 divided by 5, and that equals 2 hours. So this is the same scenario. We have a distance that light has to travel, and we know how fast it's traveling. So I can tell from this type of problem that I'm going to be doing division. That maybe wasn't exactly clear to me at first, but it is now that I changed up some words in the situation to make it more realistic to my life. So let's do division. We have our front numbers here, and then we have our 10 powers that we'll come back to at the end. So since it's division, I'm dividing out my front numbers. So I have 1.2 divided by 5.88. And just to remind you, the first number we read in a problem, we read left to right. The first number gets to the party first, so he's inside the house. And the second number that we read showed up right after him, so he is outside the house. 1.2 divided by 5.88. Not an easy number to divide by. We don't like dividing by decimals. We really just would rather not deal with them if we don't have to. So let's make this a whole number. In order to do that, the decimal has to be at the end. So that's 2 jumps over. So now I have 588 outside, and I cannot change that without also changing the position of the decimal of the number inside the house. So I moved it 2. I'm going to move this one 2 also. They have to be the same number of jumps, and that makes this 120. Okay, so where I move my decimal to is where I'm going to place it directly above for my answer part. I'm going to erase this just to have a little more room up here. So I read this at first, 120 divided by 588. If I have 120 cookies, I cannot divide them out between 588 people and get a whole number of cookies. So there is no whole amount of cookies that anyone's going to get. Obviously, when I multiply that back out, I'd get 0, so I'm left with 120. Add another 0. All right, well, here's another situation. Now I have 1,200 cookies, and if I divide that by 588, I know that for sure that people are going to get at least 1 cookie. If I think about this reasonably, this is almost 600, but it's not quite 600. So since it's a little bit less than that, I'm going to go ahead and say it's 2. And we can always check, and if we're not right, we can go back. So 2 times 8 is 16. Carry that. 2 times 8 is 16 plus 1 is 17. 2 times 5 is 10 plus 1 is 11. It works out. And I am left with 4. Gotta borrow. So this becomes a 9. This becomes a 10. You guys know how to subtract. So I'm left with 24 at this point. Okay? Because these would become zeros. So what I'm going to do now is add a 0, bring it down because I'm not done. Again, I cannot take 588 out of 240, so I don't just add another 0 and act like nothing happened. Since this doesn't give me an amount after I brought down a 0, I have to fill a 0 in, and now I can bring in another 0. And let's see, 2,400, well this one was 1,200 and I was able to get 2 full groups out back when I had 1,200. 2,400 is double that, so double 2 is 4. That should work out, let's see. 4 times 8, 32. 32 again, plus 3 is 35. And 4 times 5 is 20 plus 3 is 23. And again, if I subtract, that's the first number I can borrow from. That's going to become a 9, so that can become a 10. and I'm left with 48. This is going to continue on, it seems like, in this pattern, and that's okay. Sometimes we have very, very long decimals and they go on for a while. I'm going to end it at this point, so let me rewrite this over here. I have 0.2040, and this may go on for a while, it may not. It seems like I'm doubling each time, so it's going to be getting larger, because 12, then 24, then 48, so on and so forth. So I'm actually going to leave it at this point, and that is okay if you do that. I'm putting it in scientific notation now, so let me move it over. 0.2040. The scientific notation part deals with my 10 powers. I had 10 to the 19th, and I had 10 to the 12th. I divided. When you divide powers that have the same base, you subtract the exponents. So it's times 10 to the 19 minus 12, which is 7. Again, when I'm dividing scientific notation, and I'm dividing the 10 powers, they have the same base, different exponents, I subtract. This is a good answer. This is not the best answer because I'm not in scientific notation. So what I'm going to do now is move my decimal over one jump, because scientific notation says I need a whole non-zero digit, decimal point, and then the rest of my values. And we know it went on further than this, but we're ending it just for the sake of ending it pretty cleanly without a long decimal. If I move to the left, which you guys have been doing a lot with your adding and subtracting, it should get larger. If I move it to the right, my exponent should get smaller because we're getting closer to the end of the number. Also, a good way that Ms. Carbonell explained it is that if I'm making this number larger, my exponent becomes smaller. If I'm making this number smaller, my exponent should become larger. So by moving it over, I have 2, which is a whole non-zero digit, 0.040, and times 10 to the 1 jump to the right, 1 jump less, 6 power. So when all is said and done, here is my answer. Not the nicest decimal, but we got it, it works. Okay? So your job now, I'm going to erase this. If you need to pause it, go ahead and pause it. If you want to rewind, see how I thought about it, you can. Your job is going to be to complete these next two problems. I'm going to put the screen down just so we don't have as much of a glare. And again, you may have to pause to get all the words, to copy them as needed. So I have the mass of the sun is 1.989 times 10 to the 30 kilograms. The mass of the earth is 5.98 times 10 to the 24th kilograms. How many times bigger is the sun than the earth? How many times bigger? So again, these numbers are kind of obscure to us. We might want to use something that makes a little bit more sense to us. I might say, I weigh 100 pounds, for example. That's not true, but we'll pretend. I weigh 100 pounds, and my nephew weighs 50 pounds. How many times larger am I than him? And that should help you decide on what operation to use. Okay? Last problem. Population of Mathville, my favorite town, is 5.6 times 10 to, that is a 3, to the 3rd power. The population of Algeville is 1.3 times 10 to the 4th. How many more people are there in Algeville? How many more people? A lot of times we see that word more and we think, oh, if I'm talking about more, it has to be addition. But if I'm trying to compare how many more people are in one place than the other, it's actually a different operation. And again, I could say I have 30 students in my first period class, and I have 25 in my 7th period class. How many more people are in first than in 7th? And that should give you an idea of how to think about this one. Okay. Okay, so hopefully you paused, rewound, did whatever you need to do. I know today's video was a little bit longer, but I think I gave you a lot of thinking skills, hopefully, that you can use tomorrow when you come into class. So the last thing I'm going to remind you is making sure that you have your problem ready for tomorrow. So when you come in, you should have some sort of word problem written in words. It could be made up. It doesn't have to be realistic. You don't have to go out and figure out, the distance between your house and the park or anything like that. So come up with a word problem. There should be some sort of operation within it that isn't specifically explained. So don't use the words plus, subtract, multiply, anything like that. And you'll have your answer already planned out, but what we share tomorrow won't have the answer on it, so other people can work with it, okay? Good luck. As always, email me if you need anything, subscribe, but no comments, okay? See you tomorrow.